Hi, and welcome again to my Physics Online video lecture series. Today's video, I'm going to be talking a little bit about motion with constant velocity. So, we have previously basically described or begun to describe the idea of kinematics as the description of an object's motion, and we've defined such terms as displacement and as opposed to distance traveled, and also position. We've also defined for ourselves velocity. So you can recall that velocity was defined in terms of position versus time as average velocity is the rate change of the position, or in other words, it's the rate of displacement, delta x over delta t. Okay, that means that if I have a displacement of 5 meters to the west over the course of a motion that takes 2 seconds, then my average velocity would be 5 over 2, that's 2.5 meters per second to the west. What we want to do in today's video is kind of turn this around a little bit and ask, can we predict the position or the displacement, so maybe position and or displacement at a given time, if we know, say, the initial position and the velocity, and if the velocity is constant. The answer to this question is actually just yes. Now, there's kind of two ways of looking at this. One is to just jump straight into the equations, and the other is to make a graph. So suppose that I wanted to plot the position versus time for some motion. So maybe this axis is my time axis, this axis is my position axis. What would it take to have a constant velocity? And for that matter, how is velocity related to this graph? Well, if the position does some bit like this, then if I want to find the velocity, it's going to be essentially the slope of a straight line running between these 2 points. So slope of this line would give me the average velocity between the 2 times on the line. Similarly, if I happened to take a line that is tangent to the curve at some point in time, we'll call this time A, then the slope of this line is the instantaneous velocity at that time. Now, how do I get that slope? Well, basically in a similar way to how I would get this slope. I basically just pick 2 points that are on the line. Notice that those 2 points are not on the curve that I've drawn, but I pick 2 points on the line, and I basically do rise over run. So again, might be worth recalling that slope of a line is just rise over run. So rise over run in this case would be change in the y axis. That would be, in other words, delta x for position, divided by change in the x-axis, which is time, so delta x over delta t. If that's confusing because of our choice of putting an x on the y-axis and a t on the on the x-axis, we could always call the position y instead of x. So this is, again, position, and then down here we have time. And so in that case, we might say that this is delta y over delta t. Again, the nomenclature is whatever we decide to declare the position divided by whatever we decide to declare the time. And so again, this by definition is our velocity, delta y over delta t. You could also, of course, use delta z over delta t, depending on how many axes you want or how many degrees of freedom you want for your motion. Okay, so with that aside, slopes of position versus time give us velocities. Now, we said we wanted to have a constant velocity. So velocity is constant. Okay, what does that mean happens? Well, in terms of this graph, that would mean that for any arbitrary choice of 2 points, the line must have the same slope, or for any arbitrary choice of a point at which to take the tangent, that tangent line must always have the same slope. So how do you do that? How do you make that happen? Well, if we're going to have constant velocity, then it would follow that essentially all points have the same relative rise to run, and the only way to make that happen is for your position versus time graph, call it y versus t again, to look like this. In other words, it's a straight line. Now, the slope could be here. It could be any given straight line. So this one would validly solve this set of conditions. This one right here would validly solve that set of conditions. This one right here validly solves that set of conditions. Even a horizontal line would solve that set of conditions. It would be the special case where the slope is 0 and therefore the velocity is 0. But these are all these are all valid solutions to this set of conditions. So now we ask, what is the equation that goes with a straight line? Well, in algebra, you learn that all straight lines, y versus x, have the same basic equation, which is y equals mx plus b. So we expect y equals some slope times time plus some intercept. So if I were to draw a dash on here, I could call this intercept my initial position, and I could call this slope would be velocity. And so my equation becomes y is equal to mx, m being the slope, which is the velocity, x being t, the time, plus b being my initial position. So this is if I have a constant value of velocity. All right, so that brings us back to our original question, which we answered as a definitive yes earlier. Can we predict the position and or the displacement at a given time if we know the initial position and the velocity? And we said yes, but now we've answered it a little more completely because we have an equation which will predict for us the position at some time given a velocity, which is constant, and given an initial position. All right, so that is how these constant velocity motions basically work. We could work a very short example to kind of finish these notes for the day. All right, the train called the City of New Orleans travels at a steady velocity of 500 miles per day, beginning from, let's say, Jacksonville, Florida, which is a city that is very, very far to the east in the United States, relatively speaking. Now let's say that it travels due west for 36 hours. Where will the train be? All right, in this problem we've been given a velocity, a time, and an initial position. We're looking for a final position, or in other words, an x at this time t. So x at 36 hours, which I'm going to represent just simply as x final. And that is x initial plus velocity times time. Now the x initial we could call 0, but it's given as Jacksonville, Florida. So what we could really do is just specify this as relative to this position, Jacksonville, Florida. Or in other words, we could give a displacement from Jacksonville, Florida. So call delta x x final minus x initial. And that is going to be this velocity, 500 miles per day, times the amount of time, which was 36 hours. We need to convert that into days, so one day is 24 hours. So by the time you've multiplied all these together, you get a delta x of 750 miles to the west. Or if you prefer, the final position is 750 miles, left off the units here, it'd be miles west of, and then Jacksonville. And that is actually a complete answer, a complete final position. So that's how we do that kind of simple problem where you have a constant velocity. All right, that's all that I'm going to do in today's video. Hopefully you are feeling comfortable with doing motion with constant velocity. And thanks for watching.